So, well, today we will continue with more examples. So remember, we have defined the continuous time and discrete time convolution, and we have solved an example about continuous time convolution. So how we find the outputs for inputs to LTI systems. Today I will continue with more examples. So I have this example here. X of t is defined as ut minus 1. So this is my input. And h of t is defined as minus 2t plus 2 ut minus 1. So this is my impulse response. So I'm asked to find the output. So y of t is x of t convolute h of t. First, remember that how we find the outputs to LTI system. So y of t is simply integral from minus infinity to plus infinity, x of tau, h of t minus tau d tau. So this is our main formula. Also, please note that I can interchange x and h. So I can write it as h of tau, x of t minus tau d tau. So these are actually the same. So, but we will be mainly using this in order to find y of t. So let's first start with plotting x of tau. So this is my x of tau. So it is 1 from 0 to 1. So this is my x of tau. So please note that in the previous one, so I will find x of tau, I will find h of t minus tau, and then multiply them and integrate. So this is the main idea. Then what is h of tau? So this is my h of tau, starting from 2, and this is again origin. So what's the equation here? It is simply minus 2 tau plus 2. So this is my h of tau. Well, what about h of minus tau? Well, the equation here tells you that you will find h of t minus tau. So first I will find h of minus tau, then I will find h of t minus tau. So this is h of minus tau. It is tau here again. So it is 1 here, it is 2 here, it is 0. So it's just flipped with respect to the vertical axis. So this is my h of minus tau. So what about h of t minus tau? H of t minus tau. So this is tau here. So it is simple. So this is t here. This is t minus 1 here. So this is so the peak value is at 2. So this is my h of t minus tau. So from h of tau, first I have flipped with respect to the vertical axis in order to find h of minus tau. Then I have shifted by t in order to find h of t minus tau. So this is from t minus 1 to t, and it is increasing. This is my h of t minus tau. So what will I do? I will gradually multiply this one and that one and integrate. So first, please note that if t is smaller than 0, if t is smaller than 0, this one and that one actually has no intersection. So for t smaller than 0, I have y of t is simply 0. So for t in the interval 0 to 1, what do I have? First, let me plot x of tau. So x of tau is simple. It is here, it is 1 here. So this is my x of tau. Then I will also plot, this is my h of t minus tau. It starts from t minus 1 and ends with t. So this multiplication is actually defined only in this interval, right? So h of tau multiplied with h of t minus tau is non-zero in the interval from 0 to 1, from 0 to t, sorry. So this h of t minus tau has the formula of actually minus 2 times t minus tau plus 2. So this is my h of tau, and now in order to find h of t minus tau, I'm simply putting t minus tau instead of tau. So that's quite simple. So what is the integration? Well, y of t is actually non-zero from 0 to t. X of t is 1, so it is simply x of tau, sorry, is simply 1. It is 1 here, times simply minus 2t plus 2 tau plus 2 d tau. So it is here. So this is h of t minus tau. This is x of tau. And h of t minus tau is simply this formula here. So this is my result. So if I integrate, note that I'm actually in this interval here. Okay, this is for 0 to 1. So the previous one was for t smaller than 0. Now I'm in the interval from 0 to 1. So this is for 0 to 1. Y of t is simply minus 2 t tau from 0 to t plus tau squared from 0 to t plus 2 tau from 0 to t. If you go and evaluate terms, this is simply minus t squared plus 2t. So I'm integrating with respect to tau here. So minus 2t has the integral of minus 2t tau. 2 tau has integral tau squared. 2 has integral 2 tau. So I'm integrating with respect to tau, so t is constant. So this is my y of t for the interval from 0 to 1. So what is next? So if t is in the interval from 1 to 2, so what happens in this case? So let me draw what's going on. This is tau. This is x of tau. So it is 1. And this is my h of t minus tau. So it is t here, t minus 1 here. So I'm shifting the x of t minus tau gradually to the right. So if t is in the interval 1 to 2, then t minus 1 is in the interval from 0 to 1. So this is my main intersection of x of tau and h of t minus tau. So what's the integral in this case? The integral will start from t minus 1 up to 1. Okay, so this is the limit of integration. The term is the same. So x of tau is 1 again. H of t minus tau is minus 2t plus 2 tau plus 2 d tau. So if you evaluate terms, this is nothing but actually the same idea as above, minus 2t tau plus tau squared plus 2 tau integrated from t minus 1 up to 1. So if you solve this, actually you will find that this is simply t squared minus 4t plus 4. So for t from 1 to 2, this is my result. But t larger than 2. So if t is larger than 2, this t minus 1 is going to the right of 1. So let me draw this. So this is again x of tau. This is 1. This is 1. So this is h of t minus tau. Okay, so this is t minus 1 and this is t. So those two signals has no intersection, and in this case, y of t is simply 0. So we have seen that step by step, by shifting this h of t minus tau to the right and multiplying with x of tau and integrating, I can find y of t for different intervals. So for t smaller than 0, it is 0. For t larger than 2, it is again 0. And for the rest, I find a closed form expression for y of t. So it is quite simple to evaluate integrals and find the convolution result. So the next example tells me that x of t is 3 times impulse t minus tau, and h of t is ut minus vt minus 1. So what is the output, y of t? I will again use the general formula for convolution, and y of t is simply integral from minus infinity to plus infinity, 3 times impulse tau minus t0, u of t minus tau, let's put here, minus u of t minus tau minus 1, d tau. So the first term is actually x of tau, and second term is h of t minus tau. So instead of t here, I simply put t minus tau. So this is
Hocam sesiniz kesildi.
Can you hear me now? Okay. So 3 impulse of tau minus t0, u of t minus tau d tau. So this is the first term, minus integral minus infinity plus infinity, 3 impulse of. So please turn off your microphones. Okay, thank you. So 3 impulse of. So let's start from the beginning. I'm just going one step down. So I'm distributing this x of tau to the other terms. So 3 tau minus 3 impulse tau minus t0, u t minus tau d tau. So this is the first term. Second term is impulse tau minus t0, u t minus tau minus 1 d tau. So at this point, please remember the shifting property. If you multiply a signal with the impulse actually and integrate, the result is nothing but the signal evaluated at the impulse location. So this impulse is at tau equals t0. So the integration is with respect to tau. So I have to check the values for tau. So this impulse is at tau equals t0. So I will simply put here, instead of tau, I will simply put here t0. So this is 3 times u of t minus t0, minus, again, this impulse is at tau equals t0. So I will put here t0, and it is, again, 3 u t minus t0 minus 1. And this is in 3 parentheses, u t minus t0 minus u t minus t0 minus 1, and it is simply 3 times h of t minus t0. So if you have use the direct convolution formula, I can simplify the output as this term. Well, actually, in general, if you convolve a signal, let's say I have h of t, and this is convolved with a times impulse t minus t0. If this is the case, in general, the output is simply a times h t minus t0. So this is due to shifting property. If you convolve a general h of t with an impulse, general impulse, the result is scaled and shifted version of the input. But we have shown this actually by using formal definition of convolution. And when we find the output, it turns out that it is simply shifted and scaled version of the h of t signal. So this is, in general, if you generalize this, again, a times impulse t minus t0 convolved with any signal, let's say x of t, this is simply a times x t minus t0. So this is our convolution of a signal with an impulse. Well, in the next section, we will continue with the properties of convolution and LTI systems. Well, first we will tell you that if you have an LTI system and if you have the impulse response, you can completely characterize, you can completely determine the properties of the system by just looking at the impulse response. We will see that actually instead of impulse response, if you have the step response again exactly characterizes an LTI system. So we will also see this in a moment. But for the time being, assume that if we have the impulse response and if we have an LTI system, of course, we can completely determine its properties. Well, the statement tells you that actually if you have an LTI system, you can find the system properties, characterize its properties, whether it is memoryless or causal or whatever it is. But if you do not have an LTI system, so if your system is non-LTI, then impulse response does not completely determine the system. So here I have two examples. You can assure by yourself that those two systems are actually non-LTI systems. So let's find the impulse response. So for h1 of n, so if impulse of n is the input, then h1 of n is the output plus impulse n minus 1 squared. So I have impulse of n at the input and h1n at the output. So this is the impulse response. If I go and evaluate, this is impulse squared n plus 2 impulse of n minus 1 plus impulse of n minus 1 squared. So this is simply impulse of n plus impulse of n minus 1. So the signal, the system tells you that sum current term and the previous term and take the square. But if you check the impulse response only tells you to sum the current term and the previous term. So no square operation here. So actually impulse response does not characterize the system in this specific example. So what about the second one? So h2n is simply maximum of impulse of n and impulse of n minus 1. Okay, so this is h2n. So this result is either 0 or 1, right? Because I know that impulse of n is 0 if n is not 0, and impulse of n minus 1 is 0 if n is not equal to 1. So this result is either 0 or 1 depending on n value. So let's say for n equals 0, this is actually 1, so h2fn is 1. But for let's say n equals 1, it is again 1. For n equals 2, let's say it is 0. So in that case, again, as the original system, this h2n is not characterizing my system. So I can tell you that although for LTI systems, impulse response or step response characterizes the system itself, for non-LTI systems, this is not the case, unfortunately. Well, we know that actually we can show that impulse convolution operation has commutative property. So if you simply interchange x of n and h of n, you have the same result. So actually, if you have summation k from minus infinity to plus infinity, x of k, h of n minus k. So this is actually the actual convolution that we have defined. But as we know, I can change x and h. So this is equivalent to x of n minus k, summation x of n minus k, h of k. So this tells you that if x of n is at the input, and if h of n is your system, and y of n is the output, this is exactly equivalent to you have h of n at the input, x of n as the system, and y of n is at the output. So exactly those two executions, they give you exactly the same result. So you can prove that by yourself and assure that these two are equal. So please prove at home. Okay. The next property is associative. It's an associative property. So here I have a system H1 convolve H2. So let's tell you that this is H of n, a combined system. And if I evaluate, find H of n and find X of n convolved with H of n, this is exactly equivalent to the right-hand side equation. Again, please prove that at home. But I will now show you what does those convolution mean. So how can I evaluate them? So let's start with the first one. It is k, x of k, h of n minus k. This is equivalent to summation x of k. I will evaluate a second summation to find h of n minus k. So this is h1 of m, h2 of n minus k minus m. So this is actually equivalent to double summation km x of k, h1 of m, and h2 of n minus k minus m. Okay, so how did I write this one? This is simply h of n minus k. And what is h of n? H of n is simply h1 convolved with h2, and it is summation over m, h1 of m, h2 of n minus m. Okay, so instead of n here, I'll put here n minus k and obtain this term. So that's simple. So what does those summations tell you? Those summations actually tell you that if you have x of n at the input and you have h1n as the first system, so they are cascaded. Remember cascading. This is h2n by n at the output. Actually, in order to find the results equivalently, you can define an h of n, which is h1n convolved with h2n, okay, and find y of n. Okay, so this is exactly the same result. Also, as an alternative way, I can interchange h2 and h1. Okay, again, I have the same result. I have same x of n and same y of n. Or I can convolve as an alternative way h2 of n convolved with h1 of n. This is equal to, again, the same hn. So I have changed again h2 and h1 locations. So this is again h of x of n and y of n at the output. So actually, this associative property is quite important and telling you that instead of evaluating two systems cascaded, you can find the combined system and find your results equivalently. Okay, so please prove this at home, and the proofs are quite important. What else? The next property is distributive property. It's telling that if you have two systems summed, H1 and H2, and Xn is convolved with this combined system, instead of this, actually you can convolve the systems and find the outputs corresponding to the individual systems and sum. Actually, this is the same for continuous time systems. H1t plus H2t is equal to x of t convolved with H1t plus x of t convolved with H2t. So this is the continuous time. We have at this point an example. We have ut given, we have xt given as ut minus 1. So it is here x of t 1 t. Also, I have g of t. It is this. Okay, so I have gt given as minus 2t plus 2ut minus ut minus 1, and it is this one actually. This is, let's say, g1t, and let's say this is g1t. Okay, then I have a second system, let's say signal. Let's say this is g2t, and this is g2t. Actually, these are two impulse responses that I have defined in previous section. So now I have summed those systems, those impulse responses, and define a combined impulse response GT. Well, actually, GT is nothing but G1T plus G2T. And if I want to find the combined output YT, it is simply Y1T plus Y2T. And this Y1 here is T convolved with G1T, and Y2T is X of T convolved with G2T. And I have done those convolutions in previous sections for this signal and for this signal. So if you simply sum the individual outputs, you have the combined output for the combined system. So this is a simple application for the distributive property. Well, next idea that we will discuss is memory property in LTI systems. An LTI system is memoryless if and only if you have h of n in the form of a times impulse of n. Remember, what was a memoryless system? Actually, in a memoryless system, the output at current time instant exactly depends on the inputs at the current time instant. So you cannot use previous or future samples to find the output, input values to find the output. So it is trivial if you have this h of n, then y of n is simply x of n convolved with h of n. It is x of n convolved with a times impulse of n. And by using shifting property, this is a times x of n. So y of n is a times x of n is the only input-output relationship for an LTI and memoryless system, of course, in discrete time. For the continuous time, the idea is the same. I have a times x of t for the input-output relationship. Of course, if a is equal to 1, then I have y of t is equal to x of t, or y of n is equal to x of n. So I have output is equal to input. So I have an identity system. So identity system, output is actually equal to the input. Well, for a memoryless and LTI system, these are the only cases that you can have. The next property is causal. For a causal system, what was the definition? If you have a causal system, output at any time instant depends only on the input samples for current time instant or the previous time instant. So you cannot use future time instance to find the current value for the system. So let's start writing the input-output relationship. So y of n is simply x of n convolved with h of n as usual. This is equal to x of n minus k, h of k. So k from minus infinity to plus infinity. This is equal to, let's write a few terms, n plus 2, h minus 2 plus x n plus 1 h minus 1 plus xn h0 xn minus 1 h1 plus xn minus 2 h2 and so on. So if I expand infinitely many terms, this is what I have for y of n. So it is a summation of some terms plus x of n plus 2 h minus 2 plus xn plus 1 h minus 1 plus xn h0 plus xn minus 1 h1, and it goes on like this. So what do I need? I need that if I have a causal system to find y of n, I can only use x of n and previous x samples. So I cannot use those values because they require x of n plus 2, x of n plus 1, x of n plus 3 terms in order to calculate y of n. So this must be 0 in order to avoid future terms to be needed to obtain y of n. So I have h of n must be 0 for n larger than 0 for a causal system. So by just looking at h of n, you can tell that whether the system is causal or not. So this is a strong property for the impulse response. Well, next thing is stability. Remember, we define a stable system as bounded input, bounded output. So we require that, let's say, y of n is smaller than some value, let's say, a, if, of course, x of n is smaller than some value b. You can put here equality if you wish. So this is true for all n. So if x of n is bounded, y of n must be also bounded if you have a stable, bistable system. So if h of n satisfies this property, so if it is absolutely summable, so you have h of n, you take the absolute value of all the samples and sum. If it's a finite number, then your discrete time LTI system is stable. And this is the case for the continuous case. If you have an absolutely integrable impulse response, and in this case, again, the system is stable and LTI. In addition to LTI, it has a stability property. So how can I show this? So first, start with writing y of n. As usual, this is k x of n minus k h of k. I will put absolute sign without changing anything. I know that this is smaller than equal to this term, x of n minus k, h of k. And again, I know that this is smaller than equal to some b, because I know that x of n is bounded by some b value. This is smaller than equal to b times summation k, h, k with absolute sign. So y of n is bounded if my h of n is absolutely summable, or in other terms, this term summation k, magnitude of h of k is bounded. Okay, so this is the actually requirements that I have such that my system is stable. So we have shown that absolute summability is sufficient for stability. So if you have an absolutely summable h of n, then it is sufficient enough to tell you that your system is stable. But also this is a necessary condition. So if you are interested, please check the book for the proof of necessity condition. Okay. Well, here I have an example. I have the time shift system. So you can now by heart tell that actually this is the impulse response. Okay. So if you put impulse of n instead of x of n, you have this h of n. Okay. So let's check summation n from minus infinity to plus infinity magnitude of h of n. This is summation n from minus infinity to plus infinity impulse of n minus 2. Of course, this is equal to 1, so I have a stable system. What about the integrator? So if impulse of t is at the input, I have h of t at the output. It's equal to integral minus infinity to t, tau from minus infinity to t, impulse of tau d tau. And you can tell that, of course, this is u of t. So ut is the impulse response. So is ut absolutely integrable? So if I want to integrate from minus infinity to plus infinity, u of tau, absolute d tau, of course, this is equal to infinity. So this is not a stable system. So you can check this by yourself. This is ut, this is t. Of course, the area under this line is infinity, so this is not a stable system. So by just looking at the impulse response, you can tell whether a system is stable or not. So this is an important property. Next property is the invertibility. Remember, if you have an invertible system, if let's say h1 of t is here as the first system, and you have h2t as the second system, then x of t is directly at the output. So this is it's an invertible system. So h2t is the inverse system for h1 of t. And of course, I know that I can interchange those blocks. So h2 is the inverse for h1, and h1 is the inverse for h2. So this is the vice versa case. And we know that since LTI systems are completely determined by their impulse responses, as we have shown, we can deduce the properties such as memoryless property or stability or causality by just looking at the impulse response. So what about unit step response? So we have shown that if we have h1t, ht, or hn, we can understand the other properties for the system. So we have LTI in our pocket, it's for sure, and we can understand whether it is causal or memoryless or stable by just looking at h of n and h of t. Well, what about unit step response? Unit step response means that, so let's write, I have h of t and h of n as the impulse response, and the unit step response is defined as st or sn. So it means that for the impulse response, I have impulse at the inputs, and I have some system, and I have ht at the output. But for the step response, I have the step signal, unit step signal at the inputs, and I have s of t at the output. So, of course, in discrete case, you have impulse of n at the inputs, and you have hn at the outputs. You have un at the inputs, and you have sn at the output. So this is how we define the step response. So, as I have told already, we have seen that impulse response h of n completely determines an LTI system, and same is true for step response s of n, since h of n can be obtained from s of n. So if someone gives you s of n, you can find n. So since h of n completely characterizes a system, so does s of n. Or if someone gives you h of n, you can find s of n. Of course, these are true for continuous case, and I will show you how it is so. Well, first, you should note that you have u of n, and is equal to summation k from minus infinity to n impulse of k. Okay, so I can find u of n by summing this unit impulse signal from k equals minus infinity to n. So it tells you that actually s of n is nothing but k from minus infinity to n h of k. So this is actually due to superposition property. Superposition property. Remember, superposition tells you that if you sum the inputs, corresponding outputs are also summed. So if I sum those impulses, I can sum the responses to find the response for the sum signals. Well, here we have some tricks. Let's write s of n minus 1. This is simply summation k from minus infinity to n minus 1, h of k. And if I write this term once more, s of n is simply h of n plus summation k from minus infinity n minus 1, h of k. So if I combine those terms, I can tell you that s of n is simply h of n plus s of n minus 1, or in other words, h of n is simply s of n minus s of n minus 1. So this tells you that if you are given unit step response s of n, you can find h of n. So once you have h of n, you can characterize the system completely by using the tools that I have already explained to you. So it means that just like impulse response, unit step response completely characterizes an LTI system. Well, similarly, we have s of t as integral minus infinity to t h of tau d tau. So it means that h of t is simply d by dt s of t. Okay, so again, once I give you s of t, you can find h of t, and since h of t completely characterizes a continuous time LTI system, so does s of t. So these are just straightforward definitions, explanations that we all use. That we use is this convolution integral or convolution sum. So by just using convolution sum and convolution integral, I can prove all of those properties that we have already done. Well, next section is actually systems described by differential and difference equations, and we will try to define their impulse responses. So if you have a differential or a difference system, you can find corresponding impulse responses under some certain conditions, and we will analyze this actually. So we will be concentrating on linear and constant coefficient differential or difference equations. So apart from solving general difference or differential equations, we will be considering linear and constant coefficient differential or difference equations. Here I have some examples. So this is a linear and constant coefficient differential equation. Again, this is a linear and constant coefficient difference equation. Sorry. Well, linear because I do not have x of t, y of t multiplied with each other, or I do not have y2 squared, y2 cubed, yt squared times x of t. So I don't have such terms, so it is linear. It is constant coefficient because the coefficients here are all constant, so they are not changing with respect to time. So it is the same here. I do not have x of n multiplied with y of n, or I do not have yn squared, yn cubed, yn squared times x of n, and so on. So this is linear. Also, it is again constant coefficients because the coefficients here are all scalar, so they are constant numbers. So I will start with the discrete case. Well, assume that I have a simple differential equation, d by t yt plus a times yt is equal to x of t. Well, I know that the solution has a homogeneous part and a particular part. So if I want to solve this, yt is simply by pt plus yht. I know that this is the homogeneous part, and I know that this is the particular part. Okay, so I have both particular solutions and the homogeneous solutions. Gives me y of t. Well, I'm sure that you have gone over those in your differential equation classes or calculus classes, but we will just make a small overview. Don't worry about this. Well, this differential equation by itself does not specify a unique solution. So remember, in order to make the solution unique, I should define some auxiliary conditions or some boundary conditions. Well, of course, different auxiliary conditions lead to different differential equation solutions. So I should define auxiliary conditions or boundary conditions with my differential equation to have a unique solution. And of course, not all auxiliary conditions lead to LTI systems. Well, if you have a linear and constant coefficient differential equation, and if you have proper boundary conditions, those two together gives you an LTI system. Okay. Well, we mostly focus on difference equations that describe causal and LTI systems. Well, actually, physical systems are causal, so that's why we are concentrated with the causal systems. And of course, we are interested in finding the impulse responses for differential and difference equations that describe causal LTI systems. We are interested in this because if we can find h of t and h of n for a differential or difference equation, I can find the output for any given input. So this is the case. In order to obtain causal and LTI systems for differential and difference equations, we will assume initial rest condition. And with initial rest condition, we can be sure that our system is actually causal and LTI for a given differential or difference equation. So what is this initial rest telling you? It tells you that actually y of t is 0 for t smaller than t0, such that x of t is equal to 0 for t smaller than t0. So it is simple. If input is 0, then so is the output. So if input is 0 for some t smaller than t0, then so is the output. So output is also 0 for some t, for all t actually, for some t0 such that t smaller than t0. And this is the same for the discrete case. Y of n is 0 for n smaller than n0, such that x of n is 0 for n smaller than n0. So if x of n is 0 for some n smaller than n0, y of n is also 0 for the same interval. So this is our initial rest assumption. So this is how we define the initial rest case, okay? And this initial rest assumption actually giving me enough auxiliary conditions or boundary conditions such that a linear constant coefficient differential equation leads a causal and LTI system. So this is our requirement. Well, this section examples, I will be giving you some guidelines, some conditions, but it is best to understand this section by some examples. Well, first we will start with a very basic, very simple example and show how we evaluate and how we define the initial rest conditions? Well, first, remember, I want to find the impulse response, right? So I know that x of t is impulse of t. If input is impulse, then the output is impulse response. So, of course, for t larger than 0, I know that x of t is equal to 0. So, for sure, because impulse of t is defined only at t equals 0. So, in order to find the homogeneous solution, I will assume that t is larger than 0. So, the right-hand side is 0. So, I have d squared yt by dt squared plus 3d by dt y of t plus 2y of t is equal to 0. So this is my homogeneous equation. So homogeneous solution is the corresponding solution. So I know that solution has this form: y of t is equal to a times e to the power st for t larger than 0. So this is the homogeneous solution. And if I put this in here, I have a times s squared y of t. Sorry, y of t is actually, let me here. So a times s squared e to the power st plus 3as e to the power st plus 2a e to the power st is equal to 0. And if I have a parentheses and it's a times e to the power st parentheses, I have s squared plus 3s plus 2 is equal to 0. And I have s is equal to minus 2 and s is equal to minus 1. So what's the solution here in this case? Y of t is simply a1 times e to the power minus t plus a2 times e to the power minus 2t. So this is my homogeneous solution. Okay, I assume that input is 0, so I know that the solution has the form a times e to the power st. When I find the characteristic equation, so this is the characteristic equation, when I find and solve for the characteristic equation, I have minus 2 and minus 1 as the roots. So y of t in homogeneous form, it is in general a1 times e to the power minus t plus a2 times e to the power minus 2t. So this is my homogeneous solution. Well, of course, in order to find, so I'm okay with the homogeneous solution, or when input is 0, I'm okay with that. But what about the case? What about y of t when you immediately apply the impulse? So I know that at x equals 0, the impulse is defined. So I want to find the case at which input is applied. So in order to determine this, I have to integrate the solution from 0 minus to 0 plus. So integral from 0 minus to 0 plus d squared yt over dt squared dt plus 3 times integral 0 minus to 0 plus d yt by dt plus 2 times 0 minus to 0 plus y of t dt is equal to 0 minus to 0 plus x of t dt. Well, I know that x of t is impulse of t, so this is equal to 1. So the right-hand side is equal to 1. I know this. So I will tell you that by initial rest assumption, all of those terms are actually 0, except this one. Well, initial rest tells you that output is 0 whenever input is so. So this tells me that I can have only impulsive terms at the second derivative of the output in that specific differential. I actually impulse response. So if I evaluate this term, it is h prime 0 plus minus h prime 0 minus is equal to 1. So this is equal to 0 by initial rest assumption. So the other terms, if I evaluate the other terms here, h0 plus minus h0 minus is equal to 0. So this is 0, and this is also 0 by initial rest assumption. So what I have is this. Only the highest order term, h prime 0 plus, is equal to 1, and the rest are all 0. And by using those two conditions, I can find A1 and A2. How to do this? I know that this is the case, so I have h of t is equal to A1 times something plus A2 times something. So I will put here, I will find the derivative, put 0 and equate to 1 to find a relationship between A1 and A2. I will put 0 and equate to 0 to find, and again, a relationship for A1 and A2. Then I will solve. Actually, it will be clearer in the following examples, I'm sure. But now, remember that, or note that we are using initial rest assumption in order to solve A1 and A2. So if you have A1 and A2, you have h of t. Once you have h of t, you can find the output, or you can find the solution for this differential equation for any given x of t. Okay, we will by using convolution, right? That's simple. So at this point, we will define a method to solve differential equations. First, we have this general form. Assume that we have this general form. The first step is we determine the general homogeneous solution. So what is this? What's a general homogeneous solution? Summation dk by dt to the power k ht is equal to 0, and ht has form a times t to the power st for t larger than 0. So this is the first step. Equate right hand side to 0, puts h of t equals a times e to the power st, and solve the characteristic equation, find the roots, and find general form for h of t. Now I have to find the coefficients, just like this previous example. And in order to find the coefficients, I'm using initial rest assumption. I can use the upper way, so integrate from 0 minus to 0 plus, or in short, I can assume that all the terms, all the derivatives of h of n are 0, except the one with the higher order, just as in this one here. Okay. So I can assume that the one with the higher order is non-zero, but the rest are all 0. So, of course, using 1 and 2, I can find h of t. In step 1, I have obtained general form for h of t, and in step 2, I have find the auxiliary conditions. I have assumed auxiliary conditions, initial rest assumption, and I have obtained the relationship between the coefficients, and I can solve to find the solution. Well, in general, if you have, instead of x of t, if you have this equation on the right hand side, so again, note that it is x of t and its derivatives multiplied and summed. Once I find the, when I solve this one, the second one is easier to solve. So what you will do is first assume that right side is simply x of t and find h of t as in this one. So assume that right hand side is x of t and you apply those steps. Then simply you can find the general solution as this summation k from 0 to m bk dk by dtk h of t. So you can find the general solution. Actually, it may seem tricky, but I'm sure it will be clearer with our next example. So find h of t using initial rest conditions for this equation. So what is this? D square by dt square y of t plus 4 d by dt y of t plus 3 y of t is equal to x of t. So of course, I will assume that x of t is impulse of t in order to find the impulse response. So I assume that h of t has the form. So let me write it better. Okay. So I will of course assume that h of t is a times e to the power st, and for t larger than 0. So if it is so, it is simply a s square e to the power st plus 4a s e to the power st plus 3a e to the power st is equal to 0. So a times s square plus 4s plus 3 times e to the power st is equal to 0. So this tells me that s is equal to -1 or -3. So this is the first step. Then I will see what a1 e to the power -t plus a2 e to the power -3t for t larger than 0. And this is my actually h of t. Well, next step is, so I'm done with the first step in previous page. Now I'm with the second step. I will assume initial rest. So with initial rest, so let me write here initial rest. Initial rest assumption tells me that h of 0 plus is 0. D by dt h of t evaluated at t equals 0 plus is 1 over at. It is 1. So I will be using those two conditions to find h of t. So put here t equals 0. And what is this? So this is exactly this initial rest assumption. And what is the next? The next tells you that take derivative, evaluate at 0, and you have 1. What's the derivative of f(h) of t? Minus a1 e to the power minus t plus minus 3 a2 e to the power minus 3. Put t equals 0. And if you do this, minus a1 minus 3 a2 is equal to 1. So this is my second equation. This is my first equation. So by using those two, of course, I can find a1 and a2. It turns out that a1 is 1 over 2. So a1 is 1 over 2. a2 is minus 1 over 2. And h of t is simply 1 over 2 e to the power minus t minus 1 over 2 e to the power minus 3t times ut. Never forget this ut here, because this is our assumption here. This is our case here, okay? So since input is impulse, for t larger than 0, it is 0. So we have obtained the homogeneous solution. So ht is, after I solve a1 and a2, 1 over 2 e to the power minus at minus 1 over 2 e to the power minus 3t times ut. Okay, ut is multiplied with the whole, okay? So that's easy, quite easy. But what about the second part? If I have such an equation, d square by dt square yt plus 4d by dt yt plus 3yt is equal to x of t plus 2d by dt x of t. Now I have a general right-hand side. I have x of t and its derivatives. By using linearity property, I know that actually it is here. By using the linearity property, I know that the general solution is nothing but, let's write h gen of t, it's nothing but h of t plus 2d by dt h of t. Okay, so if you have the input plus its derivative summed, the general impulse response is obtained by h of t plus 2 times d by dt h of t, and I will write it here. It is equal to, so the h gen of t is equal to 1 over 2 e to the power minus t minus e to the power minus 3t ut plus 2 times minus 1 over t e to the power minus t plus 3 over 2 e to the power minus 3t ut plus 2 times e to the power minus t over 2 minus e to the power minus 3t over 2 impulse of t. Well, the first term is trivial. It is h of t here. The second term is the derivative of ht. Well, ht is actually a multiplication of two signals. So it is, let's say, at times ut. So how to find the derivative? Remember from your calculus course, it is equal to a prime t ut plus at u prime t. So the derivative of the first times the second plus the first times the derivative of the second, and this is the impulse of t. So this is how this impulse here coming. So this is a general way, a procedure to calculate the solutions for linear and Cauchy coefficient differential equations. So the next thing is the solutions or the impulse responses for linear and Cauchy coefficient difference equations. Well, of course, difference equations are defined for discrete time signals, and the idea is the same. I have this here over there, so I will assume that first I will solve the homogeneous one. So it is simply summation k from 0 to n a k h of n minus k is equal to 0, and this has the form hn is equal to a times r to the power n. Actually, you can omit this ak. It doesn't matter because right hand side is 0, so you can divide everything by ak and go on, and or put it there. It's based on your preference. So to find the homogeneous solution, I assume that right hand side is 0. I find the solution for summation k from 0 to n a k h of n minus k is equal to 0, and I assume that h of n is in the form a times r to the power n, of course, for n larger than 0. Next, by using initial rest assumption, actually I can have this form. Well, in discrete case, we are easy because I know that h of n is 1 at 0, so it is not infinite, or it is just a single sample at n equals 0. So by using auxiliary conditions, I can find recursively h of n. So by using those two steps, by finding h of n recursively and by finding the general solution, I can solve for actually unknown coefficients AKs. Well, if you have the general form, its right-hand side is not x of n, but some combinations of x of n and its shifted versions. Similarly, I can find exact solution linearity. So what does it tell you? The general solution is simply summation k bk h of n minus k. So this is the general solution. Again, the procedure may not be trivial, but I hope it will be crystal clear after we solve this example. Assume that I have y of n defined plus, sorry, let me. So I have y of n plus 4y n minus 1 plus 3y n minus 2 is equal to x of n. So again, I will assume h of n has the form 8 times r to the power n for n larger than 0. So I will put it here. Okay, instead of y of n, I will put h of n, and instead of x of n, I will put 0 for n larger than 0. So it is simply a times r to the power n plus 4a r n minus 1 plus 3a r n minus 2. It's equal to 0 for n larger than 0. So everything in terms of a ln minus 2 parentheses. So r squared plus 4r plus 3 is equal to 0. So r is simply minus 1 and minus 3. So the initial rest assumption tells me that, of course, h minus 1, h minus 2, h minus 3. So they are all 0 due to initial rest assumption. Okay, they are all 0. So I have from this actually, what do I have? I know that h of n is a 1 times minus 1 to the power n plus a 2 times minus 3 to the power n un. So this is my actual hn, and I know that these are the initial rest necessities. So I can solve for hn. So what will I do? What will I do is this. So could you please turn off your microphone? Some of you opened. Okay, thank you. So what I will do is I will put here x of n is equal to impulse of n. Okay, and solve for h of n just required by the method. So h of n is minus 4 h n minus 1 minus 3 h n minus 2 cross impulse of n. Okay, so this is my equation. So I know that by initial rest assumption h0 is 1. So if you put here n equals 0, h0 will be 1. So again, put here n equals 0. So you have a1 plus a2 is simply equal to 1. So this is 0 for n equals 0. This is 0 for n equals 0. So I have only h of 0 is equal to impulse of 0. Impulse of 0 is 1. So h0 is 1. And if you put it, is simply a1 plus a2. So this is my first actually equation between a1 and a2. Now I put h1. So what is h1? Again, put here n equals 1. If you put here n equals 1, h1 is equal to minus 4 h0 minus 3h minus 1 plus impulse of 1. Okay, impulse 1 is 0. 3h minus 1 is 0 because I know that by initial rest assumption h minus 1 is 0. So I have only minus 4h0, and this is equal to actually minus 4. So if you put n equals 1 in this equation, what you have is actually minus 4 is equal to minus a1 minus 3a2. Okay, there is minus here. So I have two equations. a1 plus a2 is 1. Minus a1 minus 3a2 is minus 4. So I will solve for a1 and a2. And if you solve for a1 and a2, I'm writing here, you will see that a1 is minus 1 over 2, a2 is 3 over 2, and hn is simply minus 1 over 2 minus 1 to the power n plus 3 over 2 minus 3 to the power n un. So this is my hn. So that's quite simple. That's quite easy if you apply the procedures. Well, here, please go over those problems from your book. Well, But about the second part? Let's assume that in the second part I have yn is simply yn plus 4yn minus 1 plus 3y 2 is equal to 2xn plus 3xn minus 1. And again, in this case, the general solution is simple. It is 2hn plus 3hn minus 1, just exactly replica of the right-hand side. And this is equal to minus 1 to the power n plus 1 plus 3 minus 3 to the power n un plus, I'll go from here, 3 minus 1 over 2 minus 1 to the power n minus 1 plus 3 over 2 minus 3 to the power n minus 1 and un minus 1. Okay, so this is the general solution for the given general linear constant coefficient difference equation. Well, actually, the easiest way to learn, the best way to learn this course is do this analysis by yourself. So when you watch the video and see what's going on, please exactly write the same to your booklet. So take a printout of the notes if you have not done so. So try to write those equations by yourself to have some, to get familiar with the concepts. So, well, actually, I'm not sure whether we will have Laplace and Z transforms, but those equations can be solved using Laplace and Z transforms more easily than that. Well, last thing that I will go over is the block diagram representation for difference or differential equations. This is just, to make you familiar with those representations. If you have yn is equal to minus a yn minus 1 plus bxn, you can draw the block diagram as this. So you have xn at the inputs, xn is multiplied with b, there's b here, and this is yn. So I have the differentiation, the difference term here. I have yn minus 1. Then again, there is minus a here, and it is summed. Okay, so this is how we represent in block diagram this very simple difference equation. So again, please check the book for more examples and more cases. So let me